Thank you so much, Walter. Thank you for inviting me. Thank you for being here today. Yeah, so this is joint work with Barend Spijnert, who's a PhD student in his 4th year in the Department of Econometrics and Data Science at the Freie Universität. Erik Beutner is a colleague of mine. Maybe you know him, some of you know him. And Dim Kumu is also at the FU, but he is in a different faculty. He is at the Environmental Institute, or Institute for Environmental Studies, to be precise. And so this is a collaboration between some econometricians, statisticians, and a climate scientist. And the topic is persistence of weather, more specifically precipitation, so rainfall and temperature. And we're focusing on Europe as a whole, and more specifically, actually, Northwestern Europe, so the part that we are actually all in right now. So just to give you a bit of background, flood risk is something that generally everyone's concerned about these days. There have been some very severe flood events in different parts of Europe over the last years. So the starting point of this particular empirical research is that floods do not only, but the risk of a flood does not only depend on whether there's a lot of rain at a particular day, for example, but also how long it has been raining before a strong rain event happened. So about persistence. And when this is coupled with warming, well, global warming, that is something that is happening, as we all know. In general, it can make flood risk even more severe because warmer air, so relatively warmer air, can hold relatively more moisture. So if it's warmer, if it becomes warmer over time, when a heavy rainfall happens, it tends to be more severe than in a relatively colder environment. So the warmer it gets, the higher volumes tend to be once the rain actually occurs. And as I already said, so persistence plays a role because if it rains, even if it just rains a little bit every day, the soil becomes saturated. And then when a storm comes, the more saturated the soil, the more likely it is that it cannot take the high volume of rain, and the more likely a flood actually becomes. So when we have warmer and wetter spells, or increased temperatures and precipitation persistence in the higher temperature area, so to say, this can lead to more saturated soils, which then can increase higher flood risk. So this is something that's not new. I mean, also in the climate literature, but people have mainly looked at, of course, warming trends or precipitation trends in the mean, also at variation, of course, at correlations. And in most cases, especially in the climate attribution literature, these statistical findings are often linked to what can be reproduced, so to say, with physical climate models. If there is an event, say, or there is a development that cannot be replicated by climate models, by physical climate models, it becomes difficult to, say at all what is happening and what these events can be attributed to. So, and I will come back to that actually. So what we do is we do a statistical analysis of persistence, specifically, both of warm and wet weather in winter. Warm and wet weather in winter. And we're going to first do a purely statistical analysis or econometric analysis of the time dynamics of the conditional distribution of temperature. And then in the second stage, we link the conditional distribution of temperature to atmospheric circulation conditions. And we will see that this actually makes trends towards increased persistence under some conditions even more severe. Okay, so that's the first part. So sort of this project has two parts. So there's a part about temperatures, and we're going to I'm going to show you a time-varying coefficient quantile autoregressive model for temperature. So we're going to look at specifically the tails of the conditional temperature distribution. So how the extremes, how the dynamics in the extremes change. And then we're going to look at precipitation persistence, because that is, of course, well, in a second stage, even more, say, worrying, because warm weather in winter is maybe less of a problem than in the summer. Of course, heat waves in winter usually are not so problematic for human health, at least, whereas floods are a big hazard. And as I said, warm and wet weather tend to occur together in winter. So the data set that we analyzed is from the European Climate Assessment and Dataset Project. So this is the name of the project. It's a freely it's an open source data set about almost, I think, in total 2,500 weather stations all across Europe. We made a few choices there. So we filtered the data such that, we have a time period between 1950 and 2020 available, and less than 5% missing data points overall. And with this, we get a bit more than 2,000 weather stations for which we collect temperature and precipitation volume. And we do in some ways a very simple thing. We split the data. So we take I'm going to call it old as a shortcut, right? The old part of the data between 30 years between 1950 and 1980, and the new data between 1990 and 2020. And we're basically just going to compare these two periods. So it's very simple.
Is there a reason why you have a gap in between?
So we could go as far back as 1950. So we couldn't really. So the data becomes more sparse before that. So this was sort of the natural starting point. We tried. So in some ways we want to look at as far back as possible, in the sense that, well, typically people try to compare pre-industrial conditions to recent conditions. This is, of course, not pre-industrial anymore. In a way, it's a balance between wanting to use data from as far in the past as possible and having enough data points. We repeated it though. And if you don't impose a gap, so if you go until 85 and then 86 until 2020, this things go through all the way as well. Okay, so as I said, we're gonna look at temperature dynamics first, and then we're going to also look at conditioning variables, and in particular, we're going to focus on the so-called NAO. This is called short for North Atlantic Oscillation, which is measured on a daily basis as a standardized index, and I will have it on the next slide. For robustness, we also repeated the entire exercise for two other atmospheric variables or variation indices, which did not lead to different conclusions. So I'm not going to focus on the Scandinavian pattern or the AMO, but I'm going to focus on NAO. But even if we use slightly different atmospheric variables, things are not refuted. The results are not different. So what's the NAO? It's and why do we look at it? So it is the atmospheric variable that is mostly linked to weather conditions in winter, in Europe. So it's specifically, well, it is somehow a function of a pressure difference between Iceland and the Azores or Portugal. There's different definitions, and it is a standardized index between -3 and 3. So it's an established variable in the climate literature, because it sort of summarizes two types of conditions, large scale conditions, that are called NAO plus and NAO minus. And of course, intuitively, NAO plus, we are in an NAO plus state if the index is positive, and NAO minus state if it's negative. NAO plus is associated with basically a strong jet stream from the west. And that leads generally to cooler or drier and drier weather in Southern Europe, but wet and warm weather in Northern Europe. NAO minus is just the other way around. Okay, and so this is a bit of an anecdote. This is of course not the actual analysis that we're doing, but this is just to motivate a bit more why this could be interesting to look at. So this is the end of 2023 and beginning of 2024. I don't know if you remember Storm Henk that was in early January 2024, and there were several significant flood events in Europe. So there was one in Eastern Germany, for example. There was one in Denmark, in the UK, Northern France. The Netherlands is very good at water management, but it was very critical. So there wasn't a flood, but there would have been a flood if it had just rained a little bit more. So and as I said, so NAO plus is typically associated with wetter and warmer conditions in Northern Europe, and this is actually the index over December here on the left hand side. So this flood event was really preceded by quite persistently high NAO index. Okay, now the NAO index as a whole, or the distribution of the NAO index as a whole now has shifted. So now I'm always going to refer to the old data set. Okay, so the old one is between 1950 and 1980, and it's the yellow line here is just the empirical density of the NAO index in this older time period, and the red one is the newer time period. And what we see is that basically it has just shifted to the right. So it seems that stronger positive values that were not reached before are now being reached in the recent time period. And negative ones are at least quite a bit less likely. So there seems to be a movement towards the positive range. And this is something that does not so when you run these large scale climate models, as they do in Potsdam, for example, Potsdam Institute, this is not something that they can reproduce. They do not reproduce this shift in the NAO index. So this seems to be something that is not accounted for in the conditions that are fed into these models, and therefore it's really difficult to say why exactly this occurs. Is it because of human activity, because of CO2 emissions, for example? This is an open question, but it's there. It's pretty clear that this shift has occurred. Okay. And what we're basically going to do is we're going to look at what happens to temperature and to rain if we are actually reaching positive values in the tail there that we didn't see before. right? So if we're in a high quantile of the or quintile of the NAO index, what happens to rainfall and to temperature persistence? So this is just some related literature. There, people have it's also not new to look at persistence and weather, especially temperature changes have been analyzed by Peter Phillips and Fulvia Marotta, for example. She wrote a PhD thesis about it. She's now at the Dutch Central Bank and does climate risk modeling, and also. Pierre Perron has worked on this. However, these papers focus on the mean, so the mean persistence of temperature, and we specifically want to look at the tails. And then there's a large climate literature. This is not complete by any measure on the NAO and how it affects climate conditions in Europe. Especially for temperature, for rainfall is a bit less, but people have looked at it more in a more like looking more at mean shifts and correlations and so on, not at the entire distribution of temperature. Okay, now how do we do this? Just this is just a regular autoregression. That's what it looks like. It's just a simulated path with a fitted AR1, correctly specified fitted AR1. So we can see that, of course, so it's high persistence, low noise, and everything. But of course, the fitted mean follows our time series pretty well. If we do this for a bunch of quantiles, you see that basically what this quantile autoregression can do is it can sort of provide a probability distribution for each point in time in a predictive sense. So persistence, as we define it here, is referred to as a coefficient in an autoregressive model for a quantile. And persistence is high if the coefficient is large and low if it's not. So basically the dependence of a quantile today on past realizations.
Sorry, what was the dependent variables value?
It's a simulated. It's just to illustrate quantile autoregression.
That's the idea of quantile.
Of quantile autoregression. That's it. Yeah. This is a snapshot of the temperature data for one of the stations. So this is the station in the Netherlands, in the Bild. And of course, we see the seasonal pattern in temperature that we have here in Europe. So this is something we want to take into account, seasonalities. So we're going to do that. And well, it also seems that there's quite some persistence, one could argue, by looking at it, on top of the seasonality. Now, the quantile autoregressive model we use is very standard. We're not really developing a new model here at all. It's simply an autoregressive model with seasonal components in the, well, I'm going to say intercept. So the yellow part or the orange part here could be called the intercept part of the specification, and the blue part is the persistence coefficient. And we have a constant, we have a trend to capture global warming overall, or warming overall, local warming in this case, and then we have some Fourier terms to capture these seasonalities over the seasons, and we also have a different set of these seasonality terms in the persistence coefficient to account for potentially different dynamics depending on which time of the year we're in. And I'm going to show you why this makes sense. So, or why this is actually a good idea in a second. So, but like all in all, this is just a linear quantile autoregression with some extra terms. So we can use that. We can use the usual quantile regression objective function to estimate these coefficients. The way it's written down here is in a random coefficient notation. So the randomness here comes through the UT. So that basically is a uniform. It's a uniform random variable that basically and fixing this at particular quantile. So 0.05 or 0.95 or 0.5 for the median, for example, will give the model for a particular quantile. Okay, so yeah, and if we summarize everything, this is what we get. Pretty simple. Yeah, I already said this. So we can estimate all these coefficients using any package we like. So for the Fourier terms, we tried some different values. Not strictly using information. We could have used information criteria, but it seemed that including 2 for both the mean, the intercept part and the autoregressive part seemed sufficient. So more did not lead to better fit, and less was too little. So 1 is too little, 2 seemed like a sweet spot. And okay, and now this is the graph that wants to convince you that that accounting for or that actually analyzing quantile autoregressions or quantiles rather than just the mean persistence is a good idea. So we're seeing here the estimated autoregressive functions for the build. So this is the more recent data for a set of quantiles. And what we basically see is that, say for the warmest, so this is temperature, right? So for the warmest quantile, for the highest quantile, we have pretty low persistence in the winter, but quite a bit higher persistence in the summer. And basically, so the ranking roughly between these strengths of persistence flips in the summer compared to winter, and then flips back. So here but for the median, it seems like there's not too much variation. The purple one here is doesn't move too much, but it seems that there is quite some dynamics throughout the year in the tails of the temperature distribution, conditional temperature distribution. So yeah, so this is what I said. So this is one additional motivation, maybe why we want to look at quantiles, not just the mean. Okay, but now the question is, of course, well, if this is what we find for this recent data, what about the old data? What about changes? Okay, so now this is maybe a little bit not super clear maybe to see in the back, but what we're plotting here are 3 different quantiles. So this is a 5%, median, and 95% quantile. And these are the coefficient functions for the 2 different periods that we're looking at. So the yellow ones are for the old period, the red ones are for the new period. And then there's pointwise confidence intervals here. And it's probably very hard to see the one behind the yellow line. Sorry for that, but hope you believe me if I tell you that that these pointwise confidence bands or confidence intervals overlap in the summer, but they deviate in the winter. And that is for the low quantile, so that's cold temperatures, they have become less persistent. And for warm temperatures, they have become more persistent in the winter. And on average, for the median, everything overlaps everywhere. So there it seems like not much of a persistence change. But in the tails, there is. Okay, so and this is actually also in line with what other people have found. Now, if we want to not only look at, so this was for the build again, right? So this, but now what about the rest of Europe? So this is I'm going to show you a map in a second, and what you're going to see is the differences between the old and the new coefficient. So it's new minus old of these functions in winter. So we're just extracting December, January, February here. And then we just basically take the average over these months for the estimated functions, and then we plot the difference. Yes.
Somehow the build this weather station in the Netherlands,
yes,
where it was measured. So up to now we have results measured for 1 point.
Yes.
Okay, so.
Yes, very good. Exactly. And this is now, and then this is sort of what happens if we repeat this for the entire data set. Okay, and this is for, again, for 3 different quantiles, 5%, 50%, 95%. And the dots that you see, each dot here is a weather station, and a greener dot means a more negative difference, and a redder dot means more positive, and yellow means no change. And note that this is not, we're not making significant statements here. I'm coming to this. These are really just the numerical differences between the estimated coefficients. Okay. And what we see is that for the cold quantile, we see less persistence, especially in Western Europe, also a bit in Southern Europe. For the warm quantiles, we see increased persistence in winter. So this seems to be something that not only happens in the build, but also elsewhere. So throughout. Okay. So now we bring in so this was just really just the reduced form quantile autoregression. Now we bring in these atmospheric conditions, because the idea is that, well, since NAO positive or NAO plus is associated with warmer and wetter weather, if we have this shift of the entire distribution of the NAO index, we would probably maybe be able to relate this as well to these changes in persistence. And this is what we do with basically an extension of the model, where we estimate separate coefficients for positive NAO states and negative NAO states. So basically looking at the quantile of temperature at each day, at each time point, at some tau, given conditionally on its lag and conditionally on the NAO state we're in. And we are in order to sort of disentangle the effects from the effects of NAO on persistence and the effects on NAO on just the level of temperature, we also distinguish between the intercepts, basically. So we can have different intercepts, different constants, depending on the NAO state. Again, in winter, because NAO plays a role mainly in winter. So basically we have a new set of coefficients here. We have some more coefficients than before. And then the question is, well, does it change anything? Now these are the same idea as before. We're skipping the median here because nothing happens for the center of the distribution. We're only looking at the tails, so cold and warm tail, and then we have NAO minus and NAO plus. And it seems to be the case that especially for NAO plus, the shift in the warm quantiles versus warm quantile persistence is particularly strong. And vice versa, for the cold quantiles, NAO minus the shift is particularly strong, but in the opposite direction, so shifts down. And so there seems to be, yeah, so we can actually see some association there, that if it's positive, then persistence shifts up, particularly for the warm quantiles, particularly shifts down for the cold. Okay, now significance. So I haven't talked about significance. We just saw these maps with the numbers, sort of the differences. Now the confidence intervals you saw are pointwise. If we were to do a test on every day of the year, of course we would run into a very severe multiple testing problem. So when we want to talk about significant persistence changes, we want to use uniform bands. So basically, and this is simple because this is still a linear model, and we basically have these coefficient functions are only a function of these Fourier terms, but the model is estimated linearly. The coefficients are asymptotically jointly normally distributed, and therefore we can simply construct uniform confidence intervals. So using basically using the delta method and the maximum. The maximum basically variance, the maximum bandwidth in a way, across the winter months, which is what we're interested in. So what we have is uniform confidence bands for our coefficient differences for the winter months. And we basically say that if these confidence bands are not, if there are some time points in which these confidence bands do not contain 0, then we say that the difference is significant. And it turns out that most of these differences are significant. So this is the same graph you saw before, but just without the stations for which the differences are insignificant. And we can see that especially for the NAO plus phases or the NAO plus states, in the warm quantiles we have particularly high persistence shifts, positive ones, and for NAO minus and the cold quantiles they're particularly negative. So in the winter we have less persistence in cold, but more persistence in warm temperatures. Yes.
And this central pole is median.
Yes.
So basically, at least I can interpret by median, we see almost no change.
Yes. Again, this is in line with the literature. So people have looked at persistence changes, but said, well, no, persistence hasn't changed.
You need to estimate sigma beta old and sigma beta new, right?
Correct.
What estimators did you use?
Oh, these are simply the.
Was your scalasticity robust or the usual ones, so to say? It's the power or the.
Oh, this is a good question. I think the regular ones.
In the next picture you're showing, do you estimate one regression for each point, or
yes.
Okay?
Yes. Indeed. So an interesting question would be how to do this jointly, maybe for several stations. But yes, this is really just one at a time.
Did it happen that you have quantile crossings, or?
No.
Oh.
No, but we're also not. So we focus on these 3, and for the 3, it's they're fairly fairly spaced, far apart.
On these maps, it seems that you have a pretty homogeneous pattern across Europe for the different NAO phases. In the previous ones, I think you showed before when you didn't changes between NAO plus and minus, there was like this Eastern Western European pattern. Is that related to NAO having different impact on persistence in different places?
For sure, for sure. So I'm not going. So NAO. So as I said, NAO is related to it's measured in the Atlantic, and it's related to wind the jet from the west. The further we go east, the less clear I would say the conclusions are here. We're reporting them, but I would not want to speculate too much as to what it exactly means from a climatic standpoint. But yes, I'm pretty sure that it has different implications for different parts of Europe. Yeah.
So basically, we don't care about all this like close on the right, the close to Eastern Europe.
I wouldn't say we don't care about them. So they are. So I would say they are. The effect is the same as for Western Europe, right? So the persistence. So for warmer, it's the same conclusion, right? So warmer temperatures have become more persistent, colder temperatures have become less persistent, and it's even stronger when there's, depending on the
on the left now, like a lot of results on the right. So this you wouldn't say that there's different temperature or.
So you mean this part with this part?
This part.
I'm pretty sure there is something else going on too. Yeah, these are yeah, especially for this one, I wouldn't know. I wouldn't know how to interpret this. So, but this is the cold quantiles, right? So here, the statement where the result says that also for the cold quantiles, persistence has shifted up apparently in NAO plus states. I'm not sure what that means exactly, but so in a way. What matters a bit, or what matters for the rest of the story, mostly, I would say, is that the higher NAO becomes, or the more positive it becomes, the more strongly we see persistence shifts up for warm weather, whereas we see less and less cold spells that last for longer periods.
Sorry, I think we're interrupting with a lot of questions, but
that is great. That is great. Please keep going.
2 questions actually.
Yeah.
Do you use any covariates, for instance, the altitude or where the measuring stations are located? That would be the one, and the other one is how stable is this to say, for instance, if you just take instead of an AR1 and AR2, or just add something else that's have you tried that too, or?
I think we tried an AR2 in a very early stage. So there are some. It qualitatively it does nothing. So I mean the AR. So if you include a second AR term, the first one becomes a bit lower, and then the second one there's a little bit there too, but it's not. Yeah. Okay. So I'm not claiming that this model cannot be refined further, but we did run some goodness of fit checks, and this seems to fit well in terms of getting the quantiles right. Yeah.
One last question. Is it Poland, Romania, Bulgaria, they simply don't have measurements for those, or are not reliable, or?
No, they're just not in this data set.
Okay.
It's this data set is it was a European project at some point, so they collected, and as I said, we only included the stations there that went back until 1950. So I could imagine that there are some stations that just didn't go back so far, and some others that maybe weren't part of this
Just curious. because there's-
Yeah. No, I agree. There's quite some spot, like there's some white. Yeah, I think
Well, we
Poland is
should-
particularly. I don't know. Yeah, no, that's true. It's not very. It's not super representative. It's true. Okay, so so as I said, the second part now is more about precipitation, about rainfall. So here we did something very simple. So we basically used quintile. So we chopped the NAO index for each period separately, and that's important, into quintile. So we have so 5 different regions for the NAO index. And then we just defined a binary variable that says rain yes or no every day. And so we don't want to. We tried it with volume too, but it's not very informative. So it's really so we really just focus here on whether it rains even a bit, and a bit is defined by more than half a millimeter per day. Yeah, whether it rains or not. And we estimate this a simple logit model with the lag of this binary variable and the different NAO quintiles to see whether it makes a difference for the probability of rain in which state we are, and then comparing. So that's so we're comparing all the new data again, and it seems that. And these are again, these quantiles are different for the two different time periods because the distribution has shifted. So the values on the tail in the highest quintile are quite a bit larger for NAO in the newer period. And this is the only regressor. So the 5th quintile, whether we're in the high tail of the NAO index, that makes a difference for precipitation probabilities. Or coefficient, yeah. Well, I mean, we're going to transform it in probabilities in a second. So this is the coefficient in the logit model. If we transform it to probabilities, we see the shift as well. So if we are so this basically says that even accounting for the lag, if we are in the highest state, in the highest quintile of NAO, it's more likely to rain than it was in the old time period. And this map basically shows the coefficient, these coefficient differences here. Well, no, actually not all of them, only these ones. So we focus on these ones. So given we are in the highest quintile of NAO, what is the difference in probability that it will rain on a given day? And this is what we find. So this is also so this is only the significant ones. We have that almost everywhere, at least here in Germany, Netherlands, UK, Scandinavia, we have that being in a higher NAO, in the highest NAO region, has significantly increased the probability for rain, or the persistence, say, of rain. Okay, and this is already yes.
Question about the graphic. So this is also restricted to just to the significant dots, right? Is there somewhere a number how many were significant and how many dropped out? Because to me it's difficult to see how many dots out of these 2,000 that should be there are actually in there.
Yeah. No, I see what you mean.
Dense.
No, Germany is very dense, yeah. Well, if we can, no, I don't have the number, but if I have one map where they all are shown, that's the one, yeah. So there is quite a lot, especially in Southern Europe, that drops out because of insignificance.
Okay.
Yeah, that's true. And also, yeah. So mainly Southern Europe, you don't see a difference, apparently. But
There's a question in the chat too, or the Zoom.
oh, that is a good question. Nope, nobody has said it.
No.
Feel free, yeah.
No,
I know. We'll now look again to check.
I have a question. Yeah, first, thank you very much. Maybe a little follow-up to the previous one. So you had some multiplicity control or uniform bands across across quantiles. Would it be relevant to do something similar also for the different locations?
Yeah.
Not that, the qualitative findings would be terribly different, but yeah, maybe that first.
You're right. Yes, we didn't do that though. But yes, it would. It should extend to this, of course. Yeah.
My other question that I'm more interested in. So kind of, no, not economic significance, but rather climatic significance question in this context probably. So I think I understood the logic of like why such increased persistence matters, and we see some multiplicity control or not. We surely see several statistically significant results. Like I'm wondering, like is there some way for a layman to translate like an increase in the AR coefficient by point something into like how much more does the chance, I don't know, whatever increase that the flood will be so intense that the dikes don't hold or
Yes, that's. I have that sort of in my wrap-up part. At least for floods, not for temperatures. It's a bit it's too far. For temperatures, is a bit. I mean, people can say, well, if it's warm in the winter, relatively warm in the winter, nobody's going to die, right? Maybe a few people are going to die because nobody will freeze to death or something like that. So for temperature, no, not really. So for there we don't have this, but for floods, so what we can do with these results is, for example, to say for the build, right? So conditionally on being in the upper quintile, which is in 20% of the days that we have, right? The probability of precipitation increases by 20% compared to the reference period. So if we have that's quite substantial in the sense that if you look at a month, right? So what we have as an exercise is basically the probability of having 14. Not sure why. Oh yeah, 2 weeks. Well, 2 weeks of rain within a month increases more than threefold. Conditionally on being in the NAO upper tail, of course. So these kinds of statements we can make.
Right, yeah, thank you.
Okay, so this is just a summary of the key findings, which I already.
Can you make conclusions about combinations of precipitation and temperature?
Not with this model. So sort of the common denominator we use is the NAO, and with the and if the NAO is positive and if it's high, then we have both more persistent temperatures and more persistent rainfall. So more days in a row or more days within a month where it rains. So in that sense, but that's qualitative. So it's not quantitative, and not with this model. So we'd have to use a bivariate model to make statements, joint statements. But that's a bit tricky because the distributions are quite different. The distribution of temperature. With the seasonalities and all these things versus with this rainfall, which is just truncated in the sense that it's never below zero, right? So it's tricky to model these together too. But it would be interesting for sure. But at the moment we cannot make quantitative statements at least. But we can say that since warm weather and wet weather tend to occur together in NAO positive, that is sort of the common denominator. So if that occurs, then we have also more persistence in temperature, in high temperatures and in rainfalls. Yeah.
have a question in the chat.
Oh,
Well, not in the chat, I think Christina wants to.
Yes. Can I have the question? Yeah. I wonder about the variables, the uniform distributed variables in the model.
okay.
Is it necessary to use them in the model?
So this is so you mean this model? So
Yes, no, I mean this model.
so it is one way to specify a data generating process for quantiles. It is the way that Kunker and Xiao use. Otherwise, there are different ways to do it. But if we didn't have the uniform, if the U's were fixed to a particular tau, then there would be no randomness, right? So then we would have to have something like maybe an additive error term, like a quantile error term. There's another way to do it, but this is, yeah. But when one is interested in estimating sort of quantile functions, so basically we can. So this is a different curve for every value between 0 and 1, basically. Well, this is a way to do it. So fixing the tau to different values, we can then get these coefficient functions back. So it is possible to formulate it differently. But then if there were no U's, there would have to be an error term.
Yeah, you have equivalent as
Yeah.
far as I know, representation with error or with random coefficients.
Yeah. Yeah. So this is easy to simulate from. Yeah.
Thank you.
Okay. Thank you. All right. So just one or two more things about. Yeah, this is we already said this. So just a little bit about the relationship of the attribution literature maybe. I mean, maybe you know this these kinds of statements that come in the news as well sometimes when there's an extreme weather event such as a particular flood or a heat wave. Then sometimes there's these rapid attribution studies that come up with statements such as, well, due to global warming, an event like this has become this much more likely compared to in a situation where there had been no global warming or no warming. So as I said, the way they arrive at these statements is by, well, looking at very specific conditions, very specific events, such as maybe an extreme heat wave that lasts for a week or so in a particular place, and then they really try. Then they run these physical models, and there's lots of them, and they simulate from them, and basically look at the models that can reproduce this event with and then these models are run with different initial conditions, such as a different overall temperature level, and then they can say, well, with the pre-industrial temperature level, the event would have been this likely, and now that we have global warming that is already, say, I don't know, 1.2 degrees or something above pre-industrial times, it is much more likely. But the problem is as I said, that the conditions that we are looking at here, this NAO shift, is not something that these climate models can reproduce. And therefore we cannot say what a counterfactual could be, or what the situation that we have now is compared to a counterfactual where humans, well, I don't know. If humans hadn't blown so many tons of CO2 and other gases into the atmosphere. However, something that is sometimes mentioned as a climate system that is watched critically is the AMOC, the Atlantic Meridional Overturning Circulation. which has been shown to have slowed down. It's and it's a bit, well, there are some hypothesized links between the AMOC and the NAO. But the causal relationship or the causal direction of this link is unclear. So yeah, and there are some things that one can do based on this. Yeah, including also more spatial approaches, maybe looking at how closer stations maybe have different or more similar patterns. Yeah, something that we're thinking about right now. And that's it. Thank you.